Good morning, everybody. Peace. Um, Last time, as you remember, we did the Bradford assay. I don't know if you can really see these things. Let me see. We did the Bradford assay, and in this Bradford assay, what we were trying to do is pretty much establish the concentration of an unknown solution. That was an unknown protein solution. That was the goal. But what happened was, in order to do this, we have to first create a standard curve, what's known as a standard curve. Sorry, I just kept saying that 3 times. I know, I'm aware of that, but fine. So we use the spectrophotometer. So I'm just going to give you a brief overview of how to you organize your data. Okay. First of all, keep in mind that the Bradford reagent, which is also referred to as a Comasi blue dye, is usually reddish brown in color, as you can see here. If I can zoom in there, and then once it mixes into protein, what happens is this dye is it's full of cations in unbound state. So what it does is it finds some kind of negatively charged side groups and interacts with them. Instead of doing so, it binds to a protein. When it binds to a protein, somehow there is something called conformational change. Each protein has its conformation, conformation is a 3-dimensional structure of the protein. Pretty much it's how it's folded. So when it interacts with it, nevertheless, this thing is going to with the side chains, the dye is going to change color from reddish brown to blue depending on the amount of protein you have. This is the basis of colorimetric assay. Colorimetric, so that means we are relying on the color, because the absorbance, remember, is in the visible light region of the electromagnetic spectrum. So also, as you can see here, I used some I got this. I have to tell you the source of my material. This is from DePaul University. They did a very good job of explaining this, so I'm just gonna use their pictures. So we use the cuvette, and then now what you are going to do is, if you go on D2L, each of you are going to have the mass of the protein, and for us it was in milligrams per milliliter, keep that in mind, and the absorbance at 595 nanometers. It turns out that the dye by itself absorbs at 470. When it binds to a protein, the dye is going to absorb at 595 nanometers. So that wavelengths we were working at, keep that in mind. So now then you have protein concentration in milligrams per milliliters, and then the absorbance in absorbance unit. So each of you right now, for all groups, you should have this data available to you, where you might say you go to D2L and you look at your group, see this data, and now I'm going to show you how you generate a standard curve using your data. First things first, what you're going to do is put the concentration of your protein in the x-axis. That means in the first column goes your protein concentration in milligrams per milliliter. I don't know if you can see this. I can't zoom any further. I apologize for that. And then the absorbance unit. So what you do is you select all, and then you go insert, and then you insert a scatter plot, and then you choose the scatter. Insert. You highlight your data points, highlight all the data, and then click the image, and then it says scatter. You're going to use the scatter plot. Clear so far? So first thing I'm gonna do is, I have to put in the first column my protein concentration, the standards you did from 1 to 7 in milligrams per milliliter, keep that in mind, and then the absorbance units in the second column. Then I'm gonna select all, I'm gonna highlight all, and then go to insert, and then insert chart. After that, I'm gonna plot the scatter. When you plot your scatter, oh well, I'm having trouble with adjusting. I'm using my laptop to record this. Not a very good idea. I have to get a camera person soon. Here, when you do this, then what you're going to see is that your points are going to be scattered like this. Unfortunately, folks, for you guys, your points are not gonna lie exactly beautifully on a straight line like you see this. Some will be here, some will be here, and some will be there. So they are not exactly on a straight line as you see here. Things are not perfect in real life. You know, what can you do? So you gotta work with your data. So it might not lie on a straight line like this, so do not expect it to be perfect. So then what you do next is you click on your data points. You click on one of the data points and then you say add trend line. Right click on it and then it says add trend line. Please select linear. We are trying to generate a linear line, a linear graph with a positive slope, a very good slope to it. And then also go down here and say display equation. Click on the box. I'm having this difficulty with the orientation. We get used to it. First try. Okay. So you're going to display equation. Click that one and then display the R squared value. The R squared value is going to tell you how precise you are. So it should be 0.9 to 1. Okay, if it is about 0.6, you pretty much have to go back to the original plot and start rejecting the outliers. That means the data points that don't exactly, that are out there. Like I'll show you some of the ones. Maybe if some point is lying here, if one point is lying there, one point is lying there, and then you know that these guys are definitely not gonna be on the straight line. However I try, then go ahead and remove them from the straight line. Okay, so not remove them from the straight line, remove them from the data points. So these are the outliers. So you can legitimately reject outliers somehow. So you can attribute the outliers to some experimental errors. Maybe you did not put the right amount of protein in there. So the trend line appears after you select the linear and then display equation and then display the R squared value, which is very critical. If I don't see the R squared value, I don't know how precise it is. And then you go from there. And please do not forget to label your axes. A graph that is unlabeled is meaningless, okay? So label the axes, like the y axis will be the absorbance at 595 in absorbance units. The x axis is going to be protein concentration in milligrams per milliliter for us. Also display a title for the graph. So what is the purpose of the graph? A graph is an organized way of presenting your data. So I don't necessarily have to read anything. I should be able to look at your graph and be able to get the whole picture or the whole story, okay? So that means I need the title, I need the axes labeled with the correct units, I need to see the equation, and then I need to see the R squared value. The R squared value, please look it up, is the determinant of how good your data is. So at the first try, I'm just gonna tell you I graphed all of your data. So at the first try, what you're going to find out is the data is going to be all over the place, and then you're going to end up with the R squared value of about 0.5 for all of the groups. We're not very good, but for this particular first experiment, it's okay. It's not too bad. But what I did for each group is I went ahead and rejected some of the outliers. And for all of you, actually I was able to get to an R squared value of 0.998, 0.996, something like that, which is very, very good. Okay, guys, so hopefully this is clear. If this is not clear, I'm sure there are similar YouTube videos out there on how to generate a trend line. Look them up. Internet is your friend. Um, keep learning. Have a good day.